Okay. So, today we will begin with an introduction to antiderivatives and differential equations. Okay. So, the reason why I want to do this is because it turns out that these things, differential equations, which maybe you've never seen before, are probably the most important application of calculus to real-world problems. And any of you who are, say, studying, I don't know, biochemistry or environmental engineering, at some point you're going to have to deal with differential equations, right? If you really get into the subject. Okay, these are the things that actually help you model reality. Okay, this is an important thing. Now, this is not a course on differential equations, so I'm not going to be able to go through every single one that's out there. I'm not going to be able to teach you all the great tools that there are in solving them, but there are courses for doing that. But I want to give you a flavor for why these things are important and how you at least solve some of the more basic ones. And I also want to use this to motivate the rest of integral calculus. And this is maybe a great departure from how this course is normally taught. Typically, differential equations are taught at the very end of the course and are not given a whole lot of time. So let me tell you what a differential equation is. Well, the definition is a little vague to start. So a differential equation is a mathematical equation involving derivatives. Okay, that's all it is. It's just some equation you write down that has derivatives. I'll give you the first example that always comes to my mind when I think of derivatives. So Newton, he's going to be involved with a lot of differential equations. Of course, Newton invented, a lot of this stuff. Right? And Newton's second law says that force equals what? MA, mass times acceleration. Well, I claim this is a differential equation. Why? Well, last term we saw acceleration could somehow fell out of derivatives somewhere. Right? How did you get acceleration?
Change of velocity.
It was the rate of change of velocity, right? And of course, the rate of change of velocity, okay, well, velocity is what? That's the rate of change of position, right? So if you take position and you take the derivative, you get velocity. So if S of t equals position at time t, then the derivative was velocity, right, at time t. And the second derivative, which is the derivative of velocity, right, the rate of change of velocity, is acceleration. So this means I can write MA as m times, well, say S double prime, or if you want to write it in this D notation, right, D squared S by dt squared. Or maybe I'll put t in here so we know we're talking at t. Okay, of course this A is also A at t. Okay, so you have some equation that has a derivative in it. That's a differential equation, right? Okay, it's so stupid. Okay. Let's see some other examples. Let's do some ones that seem utterly random. about d squared y by dx squared plus 4 dy dx minus 2 y equals 0. All right? It's an equation. It involves derivatives. It's a differential equation. Secant of x times y plus 4 times the derivative of x, or derivative of y, equals 5 cosecant of x. Okay, again, an equation involves derivatives. It's a differential equation. Let's mess this up a little bit. Write secant of x dx plus cosecant of y dy equals 0. Okay, now this looks a little different. This looks a little bit different. These dx's and these dy's are supposed to come together, right? Okay. Remember last term we talked about differentials a little bit. And differentials, which I'll cover again, they were a way of somehow breaking this up so that you could actually think of this as a fraction, even though right, when you first learn, you say, well, it's not a fraction. You can't think of it as a fraction. Okay, but we've learned a way you can think of it. So you could break these up. Well, anytime you see these dx's, right, you think, okay, that's a differential. Differential is very close to derivatives. Okay, sorry, same thing. Okay, all right. So again, we're going to call this a differential equation. Okay? There's a special one called separable. Okay. Okay, so these are all differential equations. Now, when mathematicians talk about differential equations, there's kind of an in and an out. The in, right, is there's some situation which is creating that differential equation. Okay, they see something in reality that tells them something like this should be true. Newton says, oh yeah, there's somehow when I do all these experiments, there's a relation between the force and the acceleration, right? And it's just proportional to the mass somehow, right? Okay, so he writes down this differential equation. And in biology, they have, for instance, the predator-prey model. Okay, so you imagine we'll talk about this a little more later, but imagine you have a very small ecosystem. It has one predator and one prey. Okay, and the prey eats something, but the prey what it eats is outside the ecosystem somehow. We don't worry about that. Okay, now if there are fewer prey around, what's going to happen to the predators? They're going to die out, right? If there's fewer prey to eat, they're going to die out. Okay? If there's more predators, what's going to happen to the prey? They're going to die, right? The predators are going to eat them all. Okay? So you already in your head have some ideas. Oh yeah, okay. If you increase predators, prey will decrease, right? If you decrease prey, the predators will decrease also. Okay? So there's these relations. Okay? Now, whenever you have relations like that, where things are going up and down, you start thinking, ooh, there's change involved. And whenever there's change involved, you should think rate of change. And when you think rate of change, what do you think?
Derivative.
Derivatives, right? Rate of change, we think derivatives. Okay? Okay, so that's how these differential equations are starting to show up in the real world. Is you just see change happening all around you. Everything in the world is change, right? So differential equations, that's what's modeling change, because this thing measures change. Okay? Okay, so that's the in. What's the out? Well, the out is somebody says, yeah, okay, fine, but what's that function? Right? Maybe I know this differential equation holds, but what's s? I want the position. I don't just want to know what the acceleration is. I want to know what's the position. So I need to find some s which makes this true. Some position function which makes this true. Okay? That's the out. That's the solving of differential equations. Okay? And so that's what we're aiming towards, is figuring out, okay, how can we actually solve these things? Now, if you write down an arbitrary differential equation, you can make them arbitrarily difficult. Right? And you can maybe not solve most of them. But we're going to try to at least write down a few that we could. So let's start with one that we can, a classical differential equation, one which our departed brother Tom talked about in his final project last term. And then again has to do with relating position, velocity, and acceleration. Well, actually, we may not even need acceleration for this. Okay, so we use this only because the numbers are so weird that I don't remember them. All right, so let's assume we have a rocket ship. Okay, most of us have those. Okay, so we have some nice rocket ship flying through the sky. We were just watching the Superman movie, the very first one, not the new remake, but the new one. I mean, the old one. And, Superman goes after these rockets that Luther's firing at California. Okay, so let's say that, well, we're always going to assume in this example that time is greater than or equal to 0, or some starting point, and the rocket's velocity. Right, so v of t, the velocity of the rocket, is given by the following equation. 30,000 t squared minus 1,500 t plus 12. Okay. So this tells us when we start the clock, time equals 0, the rocket was already going. All right, it's going 12 meters. So this is in, say, will be in meters per second. Okay, so it's already going 12 meters per second when we start. And let's say also we know that 5 seconds after we start, the rocket is 10 million miles. Wow, that's horrible. I gotta change that. Kilometers, all right, from Earth. So when I say the position, okay, I'm saying that the distance between where it is and Earth. Okay. So five seconds into it, it's 10 million kilometers from Earth. Okay. So I would like to figure out the position function. Okay, I'd like to know at any given time how far away it is from Earth. Right. Well, what I do know is, well, the velocity function. And I know that the velocity is
derivative of position.
Derivative of position, right? So I know that the derivative of position with respect to time is equal to, well, it's the exact same function. This means I have a differential equation. So I want to solve this differential equation. What does it mean? Well, it means I need to find some s such that ds dt equals this bizarre thing. Okay. So let me write down an s for you, and then we'll check. Right? We'll verify that it is a solution. Let's write down 10,000 t cubed minus 750 t squared plus 12t. Okay. Does this position function satisfy this differential equation?
Yes.
Sure, right? We take the derivative. You get 3 times 10,000, 30,000 t squared. 2 times 750 is 1,500. Good. All right, derivative of 12t is 12. Beautiful. Okay, but here's the problem, right? That would also be a solution to the differential equation, right? Because, well, derivative of 1 is 0, so it doesn't change anything. Okay? And if I had a 5 here, same problem, right? That also will be a solution to this differential equation. And of course, for any constant c, okay, this will be a solution to the differential equation. So this is a solution to, let me give a symbol star for this line. It's a solution to the differential equation star for any real number c. Okay, so for those of you who weren't around, that means is an element of, that's the set of real numbers. Okay, so c is a real number. C is an element of the real numbers. Okay. Okay, so this is already quite nice. We we have a bunch of possible solutions. But here's the thing, they can't all be right, can they? Why can't they all be right? Well, I'll give you a hint. If I covered up this line, they could all be right. Right? Only one of these should have this, right? Or, well, maybe there could be more than one, yeah? Maybe for different C's you could think, oh, well, yeah, okay. Maybe S of 5 could be this, but then you think, oh, wait, adding constants. No. If one of them works and then I add something to it, it can't work anymore, right? Okay, so only one of them can work. Okay, so let's see which one. Okay, so we have an equation, and we want to test whether or not it satisfies this initial condition. So this says when t is 5, we should get out 10 million. So we plug 5 in. So 10,000 times 5 cubed minus 750 times 5 squared plus 12 times 5 plus c should equal 10 million. Okay. Now this is far too complicated a computation for me to actually have anybody do without the benefit of numerical aid. So I'll just tell you what you get. So if you compute this out and then subtract it to solve for c, you will get the number 876, 8690. And so this tells us that S of t should be 10,000 t cubed minus 750 t squared plus 12t plus, what is that? 8,768,690. Okay. All right, so let's give a few names to the things we just did. When we came up with this kind of general solution, that just had a plus c, we give a special name to that general solution. We call it a general solution. You would not need this initial condition to come up with this general solution. Now, once you get an initial condition, then you're able to find, well, sort of a particular solution. And so we give a special name to the particular solution. We call it a particular solution. So when I ask you, here's a differential equation, find me a general solution, I'm asking for this. Okay? You're tipped off that it should have either a plus c or some constant somewhere in there, maybe times c, depends. And when I say a particular solution, there should be no unknown constants. Okay? You just should have your maybe one variable. Okay, now, there's a very good question to ask at this point. Certainly, once I have this general solution, this is the only particular solution to this general solution, given this initial condition. Agreed? No other way to do it. Once I start with this general solution, right, we solve it. There's just one C that works. Okay? But that's assuming that I have just one general solution. Right? There could be another solution, right? Okay. We're going to show later on, and those of you who took my final last term actually already did, we're going to show that this is the only possible general solution. See, do you like the way I did that? Your last question on your final was the springboard into this course. Isn't that nice? Okay, so Let me do another example. Any questions actually on this example? It's reasonably straightforward, yeah. It's just calculus. No problem. Okay, so let's do this. Let's define, well, I won't tell you what this is coming from yet, but n of t, when I use that, I'm usually thinking of the number of something. I don't want to say this. So n of t is a function satisfying the following differential equation. Derivative of n with respect to t should be t to the minus 1/2, right? Or if you like 1 over the square root of t. Okay, now last time when we had the rocket ship going, okay, we assumed that t was greater than or equal to 0. What should I assume here? It better be greater than 0. I'll just add that up there. So I'm only going to look when t is greater. Okay, fine. No big problem. And let me also add on, well, we don't know, I mean, well, I should put this t greater than 0 next to the differential equation. Let me say also, at 0, where we're not supposed to know anything, it's 60. And we assume all sorts of nice things in this class about our functions so that they're easy to handle, because we're not here to do math in its most general form. So we just, anytime we need something like, oh, this function should be continuous at 0, differentiable at 0, whatever, we just assume that to make things nice. So we assume this is continuous at 0. So this condition is going to jive with what's above it. Okay, so what's n of t? Let's solve this differential equation. Well, I need to find a function whose derivative is t to the minus 1/2.
Multiplied by t.
What's that?
We're going to multiply it by t. So
We're going to multiply by t?
yeah, so minus 1/2 plus 1, which is 1.
So what you're saying is, okay, when we take a derivative, right? If we end up with a minus 1/2, well, probably when we started, we had a what? A plus 1/2, right? Because when you take a derivative, that power goes down by 1. So we know there probably should be a t to the 1/2 here. But now here's the thing, right? When you took the derivative, that became a 1/2, but it should end up as a 1. So I put a 2 here. Right? So we just check again. Okay, 2 times 1/2 is 1. Subtract 1, you get negative 1/2. Cool. So that's one possible solution, but what's the general solution? Plus c, right? For any constant c. So this will be the general solution. Right? Okay, but we also have this little extra bit of information. We know that if we plug in 0, we should get 60. So 2 times 0 to the 1/2 plus c should be 60. Cool, that's easy. What is c? 60. Awesome. Okay, so this tells us that n of t equals 2t to the 1/2 plus 60 is our particular solution. Okay. So, what was annoying when we wrote this problem is that we got to this and we started having to guess. We started having to think. We hate thinking, right? I mean, what a drag. So we said, oh yeah, if we add 1, well, we got to correct, we got to put this 2 in there. Okay, it all worked out. But you can imagine if I made this worse. Right? I could just make this a little bit harder, and every time I made it a little bit harder, it'd get more annoying. Okay, so one of the things we're going to do in this course is try to come up with ways of figuring out functions whose derivative isn't a function that you want. Okay? That's going to be called the antiderivative. And we're going to talk about that a little more now. So I just want to maybe say something a little more abstract than you're used to. If I give you a differentiable function, right, and let's say you're the derivative. You're the derivative. And I throw differentiable function at you, you take it, and what do you do with it? You catch it, and then you're the derivative, so you differentiate it. Right? And then what do? You throw it back to me, right? You're being polite, you throw it back to me. Good. And what do I have? I have a new function. Okay. So I gave you a function, you gave me back a function. You're kind of like a function, aren't you? Right? What does a function do? I give you a number, you spit out another number. Okay, so the derivative is a function. It eats differentiable functions, and it spits out new functions. Okay, that's nice. Okay. Not only that, but it satisfies all sorts of cool properties, right? If I take 2 functions and I add them up and I give them to you, right? Do you have to add them up first and then take the derivative, or can you? What else could you? You could do them separately. Take the derivatives and then add them up and throw it back. Right? Or you take the derivative 1, throw it back. Take the derivative 2, throw it back. Right? Okay, you can do it one at a time. Right? If I multiply one of my functions by a constant, you can first take the derivative, throw it back, and then hit me with the constant. Right? You can do all these things. So it's a very nice function. It's called a linear function. Okay, so this is already very, very nice. There's a lot of good things going on. Okay, now every time you have a function, say e to the x, sine of x, right? X squared, x cubed. What's a really nice thing to look for along with that function? For instance, e to the x matches up very well with a certain other function. The natural log. Okay, and sine of x matches up very nicely with
What?
Cosine?
cosine is a good function to match it up with, but it doesn't match in the same way that e to the x and ln of x matches up. Arcsine, right? What's the relation between these?
The inverses?
They're inverse functions.
They cancel each other.
Yeah, they cancel each other out somehow, right? If you do one and then the other, it's like you did nothing, right? It's the whole, you watch your movie and then rewind it, for those of you who know what tapes are. Okay, it's like you didn't, nobody knows, right? You know, my wife goes out of town, I put on that old movie that I'm not supposed to watch, you know. I watch it, then I make sure I rewind it, put it back in the shape. No, nobody's the wiser, nobody knows, right? Inverted. Okay. So anytime you have a function, you should ask, does it have an inverse function? Okay. And of course, the thing you're looking for is, right, it needs to be 1 to 1. That was always the point. Okay. If you had x squared, this had an invertibility problem. Right? You can't invert x squared. Because, well, when you find the inverse function, right, it should just do everything backwards. Right? So here, let's say we had 2. 2 goes to 4. If you go backwards, it should send 4 to 2. But where does 4 get sent to? Well, you don't know. It could go to 2 or it could go to -2. Who knows, right? The inverse isn't a function. Now, we had ways of getting around that, right? We restrict the domain, right, to arbitrarily make it 1 to 1. But generally speaking, x squared doesn't have an inverse. Okay? And the reason why is because it's not 1 to 1. Okay. So, what about the derivative? Derivative is a function. Does the derivative have an inverse? Right? Is there some function, I send you the derivative, right? And then when you throw it back to me, right? I send you the function, right? You throw me back the derivative, and then I say, I just turn it right back around and give you back the original function. Can I do that? Okay. And strictly speaking, the answer is no. You can't do that. Okay. But You're only missing it by a little bit, namely a plus c. Okay? I can give you back the original function up to a constant. And when I do that, that process, right, the opposite of differentiating is called anti-differentiating. Okay. So let me give you a more formal definition. All right, so let's let I be an interval. So remember, an interval, right, just some continuous segment on the real line. I don't care if it's, got the parentheses on the end or the square brackets, or it could be half closed, half open. I don't really care. Just some interval, right? -1 to 4. Could be an infinite interval. Could be 0 to infinity. Doesn't bother me. And let's let f of x be a function on that interval. A function capital F of x is an antiderivative and in parentheses, let me write with respect to x. This will become more apparent why I write this later. With respect to x of f of x on I. Okay, so it's an antiderivative of f on this interval if the derivative of capital F is little f. For all x in the interval. Okay? So you're just, an antiderivative just says find some function, right, which gives me back my function as its derivative. Right? It's like an inverse. But of course we know there's not going to be just one of these, because as soon as I find one, I can find more. If f of x works, what else works? What is another antiderivative? So if f of x, capital F, is an antiderivative of my function, can you find me another antiderivative?
F minus.
How about f of x plus 2? If I have f of x plus 2, and I take the derivative, what do I get? Well, derivative of 2 is 0, so it's like it wasn't even here. I get f of x. And of course, there's nothing special about 2 other than that it's some real number. You can put any constant. So this is already kind of sad. It would be really nice if there was just one antiderivative for a function. There's only one derivative for a function. Why shouldn't there be one antiderivative for a function? But no, alas, once you get one, you always get plus c. Okay, so what's the next best thing? Well, the next best thing is if this is bad as it can get. Right? Let's say you find one of these, then you say, okay, I have plus c. Good. Okay, I know. Okay. But then somebody else turns around and says, I have a completely different function. It's a completely different antiderivative. And you say, well, no, I mean, they must be different by a constant. He goes, no. It's a completely different function. Okay? That would be really bad. Because then how do you know that you're even done looking for those things? Okay, so we're going to prove that that can't happen. You're in the next to best possible case. So we're going to have to use a little bit of theoretical hoo-ha in this proof. Just bear with me on it. It'll be short. It's like lethal injection, only you guys aren't going to die. You'll have to see more of it. Okay, it's going to come in two parts. So the first part is what was the last problem on your final last term. The second part is really just a corollary. Okay, so do I need any... Probably not. Yeah. So let's let... Now, okay, the hypotheses that I'm going to put down here, we're always going to have. You don't have to worry about them. They're only in there so that I can use the mean value theorem later on. Okay, so don't worry. Don't be scared off by these hypotheses. Okay, I'll tell you what everything means. So let f be continuous on a closed interval AB. Okay, closed meaning we include the endpoints. Okay, and A not equal to B, say. Okay, what else do we need? We probably need a differentiable on the open interval. Yeah. And differentiable on the open interval AB. Okay, so again, don't worry about this. Is just stuff to make mathematicians really excited. And now here comes the interesting hypothesis. Right? So I have a function on some interval, which when I look at the derivative on that interval, it's always 0. So this is for all x in the open interval. So I just look on this open interval AB, and it's always 0. Right? The conclusion is, well, what should the conclusion be? The hypothesis, the interesting part, is that I have a function which, on some interval, has 0 derivative. Now, what function has 0 derivative? A constant function, right? So that would be the best thing, right? Remember over here, this was kind of a problem, right? If we had an antiderivative, we knew we could always add c, and we get another antiderivative. But it would be really nice if this was the only, the only antiderivative up to a constant. Okay? We'll replace f of x by the 0 function. Okay? It would be really, or not by the 0 function, sorry, excuse me, replace this f of x by the 0 function. Okay? It would be really nice if that meant that all we started with was a constant, because that would somehow be that would be the first good step. So that's the conclusion, that this function is constant on the interval AB. Period. Okay, so let's prove that. The proof is not so complicated once you accept the mean value theorem. So if we want to show that a function is constant, we just need to show that at any 2 points you get the same value out. Right? So constant means, so no matter what number you put in, you get the same number out. So let's take 2 numbers, x1 and x2. Okay, somewhere in this interval. Okay, and they're just different numbers. Well, let me just say the hypotheses of the mean value theorem. Okay? The mean value theorem looks for functions which are continuous on a closed interval and differentiable on that on the open version of that interval. Okay? And when you have those hypotheses, right, well then what did the mean value theorem say? It said something like this. You take 2 points, right, x1, x2, and you draw the secant line through those 2 points. And it gives you some slope. Okay, and that's the average slope. I mean, that's the slope. That's the average velocity, right, from here to here. Okay, and the mean value theorem says that there's some point somewhere there where if you draw the tangent line, right, the derivative. Oh, I didn't even get close. Where's it going to be? What it's saying is that there's some point where when you draw, there we go, right about there, the tangent line, you actually get the same slope as the secant line. That should be parallel. That's all it says. So, by the mean value theorem, well, take our points x1 and x2. Right? If you want to know what the slope of this line is, well, it's just f of x2 minus f of x1, right? That's y2 minus y1 over x2 minus x1. Okay, so there's that average slope. And the mean value theorem says that there's some point in between, call it little c, such that the slope of the tangent line, and of course, how do you get the slope of the tangent line? That's just derivative. Okay. The slope of the tangent line, or the derivative at c, equals the slope of the secant line. So for some c in between x1 and x2. Okay, so that's the theoretical part. And now comes the fun part, where everything just collapses under the weight of 0. Right? The hypothesis of this statement is f prime is 0 anywhere on the interval AB. So what is f prime of c? It's 0, right? C is somewhere in between x1 and x2, but I mean, look, A is here, and x1 is here, and x2 is here, and B is here. So C is somewhere in between, so it's definitely in between A and B. Right? So the derivative, which is always 0 on AB, must be 0 at C. So this is equal to 0. Okay, now you have a fraction. The denominator is definitely not 0, because x1 is not the same as x2. And if you have a fraction equal to 0, what does that say? The numerator is 0. Okay. So f of x2 minus f of x1 is 0. Add f of x1 to both sides. Okay, f of x2 equals f of x1. What does that say? It says, doesn't matter what values I put in, f treats them the same. It spits out the same number. That means f is a constant function. Okay? That's what constant means. You put in the same different numbers, you get the same thing out. So f is constant. The little squiggly square box that says end of proof. Okay, that's what we want. F is constant. Okay, so this tells us that at least in one case, right, when the derivative is 0, then there's only one antiderivative up to a constant. What about the rest of the functions? Well, now it's really easy. It is so slick. So easy. And this is actually a pretty ubiquitous theme in mathematics of first proving something for the 0 case and then showing that everything somehow resolves in the 0 case. Corollary. Okay. I want to keep the same hypotheses as before. Okay. Except for the very last one. Yeah. Okay. So assume I have two functions, big F and big G. Okay, so assume that f of x and g of x are antiderivatives of f of x with respect to x. I won't write it. On some interval AB. Okay? What do I want the conclusion of this to be? What I'm trying to get at is I want that I only get one antiderivative up to a constant. Okay? So if I have two antiderivatives, they should actually be the same up to a constant. And that's what we do. Then g of x equals f of x plus c for some constant c. Actually, I guess that's strictly speaking the comma, and that should be lowercase t. Okay, so this is really what we want. Is yeah, you have to deal with this up to a constant business, but there's only one up to a constant. So let's prove it. This proof is very easy. We know that the derivative of f, big F, is little f, because it's an antiderivative. We also know that the derivative of big G is little f, because it's an antiderivative. Of course, if two things equal a third, then they must equal each other. Okay, so these have the same derivative. Now let me subtract. Okay, so if I take f prime of x minus g prime of x, I get 0. But, you remember what we said, John? The derivative is a really nice function. Why is it nice? Because it's linear, right? It breaks up over sums, right? You can pull out constants. Well, here I have a sum. Looks like it's different, but it's a sum. You can think of it as plus, minus, whatever. This is the same thing as first subtracting and then taking the derivative. Right? If you take the derivative minus the derivative, it's the same as first subtracting and then taking the derivative. Right? That's what linearity is. Okay? So I now have a function, a new function. F of x minus g of x, a new function. When I take its derivative, it's always 0. Now, what happens? If I have a function whose derivative is always 0, that tells me that that function is constant. If I have a function whose derivative is always 0, so there exists some constant such that, st means such that, f of x minus g of x equals c. Oops, I realized I put my things on the wrong side. Here. We'll fix this. Now nobody's the wiser. Okay, now I add g of x to both sides. Of course, it doesn't matter, right? I can move a constant one side to the other. It's a constant. So f of x and g of x plus. Voila. What luck. Okay, so this is very cool. This is very cool. Let's see. Any questions? Yeah, the proofs are nice. They're nice and short. That's why I showed them. The idea is the important thing here. Right? The idea is there is just one antiderivative up to a constant. But you cannot forget up to a constant. There is always up to a constant. 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 It's always going to be there this whole term. Those of you who took the course before know that this plus c is serious business. Right? You always have to remember plus c. And when you don't, what does your teacher do?
Minus 1.
Gets the ruler out and whacks your hands, right? Okay. Always plus c. Okay, so let's start one more thing today. Yeah, let me define one little thing. So I want to give you a little bit of notation to go home with. And this notation goes back to Leibniz. So we learned a lot in these presentations at the end of last term about the history of calculus, right? Remember there were two main founders for calculus, Newton and Leibniz. And Newton, he was thinking about everything in terms of physics. And he had all his nice problems, and he was just a brilliant guy. And Leibniz, he was, I don't know, he had been a very good publicist today. And he understood how you actually got mathematics out to the masses so that they could use it. And part of what he said is important is to have good notation. And so most of the notation that we will use in this course is due to Leibniz, not Newton. But the ideas are almost certainly date back to Newton. Okay, so what's the notation I'm going to give you? So this is a highly non-standard definition I'm going to give you, but don't worry about it. I'm going to experiment a little bit this course. You guys are my little lab rats. That's kind of how I view you. That's not nice. Okay. Okay, so let's just take any variable. I'll call it x, but it could be anything. It doesn't have to be an independent variable. It could be independent, could be dependent. I don't care. Any variable. We'll make the following definition. Define, okay, we use this sign, which is called the integral sign. We define this sign. Okay, if I do this integral sign and then I write dx, this is always going to be a set of functions. Okay? It's going to be the set of all functions of the form x plus c, okay, where c is any real number. Okay, this is not normally how you see things when you do this. Normally, the integral is some function, right? Just something. You don't put these sets in. And the truth is that we're not going to write it this way for very long. Okay, we're going to immediately start just writing it as x plus c. But I really want you to get that when I write this, right, when I talk about antiderivatives, I am not just getting one function. I'm getting a whole set of functions, one for every real number. Okay. I think, yeah, it's later that I'm going to go further with this notation. Yeah, so I guess I could do it now. Okay, let me do it now. Just very quickly, right? Yeah. We've told 15 after? Or 10? Yeah? Okay, 15. Very good. So let's recall that if u is a function of x, we define the differentials, right? Dx and du. So dx is just some independent variable. Okay, it is what it is. You can make it anything you want it to be. But du is a dependent variable. Okay, strictly depends on dx. Okay, and you remember the relation? Du equals the derivative of u, right, u prime, times dx. Okay, so we define things this way. And remember, the nice thing is if you define things this way, then if you divide by dx, you get du divided by dx equals u prime. So it all somehow matches up what we want, right? The derivative should be the derivative. Good. Okay. Fine. So with this in mind, let's let f of x be a continuous function. Okay, maybe we need more. But like I said, our rule is we always have enough hypotheses to do what we want. Let f of x be a continuous function. And big F of x an antiderivative. Of f of x. Okay? Then, well, by definition, df is equal to f prime dx. And f prime is what? Little f, right? Because big F is an antiderivative. So this is equal to f dx. Okay? Now, let's say I want to define, right here, I mean, I just have the integral of dx. What if instead of the integral of dx, I want to define the integral of some function times dx? The integral of some function times dx. Well, it should be the same as the integral of df. Because these are equal. And of course, we defined what the integral of df is. Right? It's just f plus c. Right? C runs through all real numbers. I need more space. Okay. So the integral, we'll read this, the integral or the antiderivative, either one, of f dx is defined as the set of all antiderivatives. Okay? I do it this way because I want you to understand why this notation, I mean, okay, you have this s, which we don't understand why yet, but why this has a dx on the end. Okay? That always confuses people. They say, well, why don't you just write it like this? Okay? You seem to have the same information, right? But here's the thing. You remember when I first defined the antiderivative, I had this little expression, with respect to x. Okay? That's where this is coming in. I could change this to a different variable, and it's going to change the whole system. Everything's going to be completely different. I need an antiderivative with respect to x. Okay. So that's where this notation is coming from. Okay? And, well, what does that kind of look like, by the way?
Yes.
Yeah. So later on, we'll see why it's looking like that, and I'll basically teach you how to know this from a hole in the ground. You got to work on that one for a while. Let that simmer. Okay. So I will see you guys tomorrow. We have the shorter 50-minute lecture tomorrow. Try to do homework 1 as soon as possible. Okay, it's due on Friday, but the sooner you do it, the better prepared you'll be for what's to come. So tomorrow we will go deeper into differential equations, define some nice terms, start a classification.